Okay, so who here is either familiar with object-oriented programming or has used object-oriented programming in the past? Okay, so some of you. How many have used object-oriented programming in R specifically? A little less of you. Okay, cool. So today, during this presentation, we're just going to talk a little bit about, first of all, what is object-oriented programming and why should you use it, when should you use it, and then what are the different kinds of ways to use object-oriented programming in R specifically. So first of all, what is object-oriented programming? Object-oriented programming is basically a paradigm of organizing your code around commonly reused data structures and ways of organizing data called classes, and then functions that are related to those kinds of data called methods. So what is a class? A class is just a blueprint for some way of organizing data. So for example, if you work a lot with proteomics experiments, then you might write a class that represents a proteomics experiment. An object is a particular instance of a class. So for example, if you have a class for a proteomics experiment, then a very specific proteomics experiment, such as the twin case study data set that Seung-Haeng was discussing earlier, that could be a particular instance or object of that proteomics experiment class. With object-oriented programming, you can also use inheritance, which allows subclasses to specialize superclasses. And we'll talk a little bit more about what that means. But just for an example, say you have some kind of class that represents proteomics experiments, as I said, and you want to specialize different classes for, say, it's a DIA experiment versus an SRM experiment. So you might have different subclasses of a proteomics experiment class that represents DIA experiments or SRM experiments or other different kinds of proteomics experiments. And finally, a method is basically just a function that's associated with a particular class. So it changes its behavior depending on what kind of object you give to it. And in R, methods are implemented using something called generic functions, which is a little bit different than how other languages sometimes use object-oriented programming and methods. So things are a little bit different in R if you're more familiar with object-oriented programming from, say, Java or C++. So we'll talk a little bit more about the differences between how methods are implemented in R in a little bit. So for example, in R, plot is a generic function. So when you call plot on some kind of object, it changes its behavior depending on what kind of object you give to it. So for example, calling plot on numeric data will behave differently than if you call plot on some kind of categorical data. So just a simple example of what this kind of class organization in object-oriented programming is like. So consider, for example, that you want to write some kind of pet simulator game where you just have like dogs and cats, and your users interact with these dogs and cats, and they're the user's pets. So you want to write the code for this kind of pet simulator game, and you need something that represents, first of all, these pets. So you might write an animal class for representing these pets. And an animal class could have subclasses cat and dog because those are specific kinds of animals. You also have different kinds of pets might speak to you, for example, in different ways. So like if you have a parrot, it might actually say something to you in English, which can be sometimes kind of weird. But if you have a cat or a dog, it might just do things like meow or bark at you. So you could have a generic function called speak that does different things depending on what kind of object it is. So you would have a generic function called speak, which is something that all of your pets or all of your animals do. And then you have an object named Mittens, which is an instance of a cat class. And if you ask Mittens to speak, Mittens will say meow. Conversely, if you have an object named Duke, which is an instance of the dog class, and you ask Duke to speak, Duke would say woof, because the dog class and the cat class each have their own methods for this generic function speak, and so speak will change its behavior depending on whether you give it a cat or a dog. Does that make sense to everyone? Please stop me if you have any questions or want me to slow down or just want more elaboration on anything specific. So how does this object-oriented programming work in R? So in R, there are two major object-oriented programming systems. The first one is called S3. If you remember when Jan was talking about the origins of R actually comes from a language called S. And so the S3 object system was implemented in the third version of S, which is why it's called S3. And later on, there is another object system added to the S language in the fourth version called S4, which is where the names of these different object-oriented programming systems in R come from. So there's S3 and S4, and they can be used for different things depending on what exactly you need out of your object-oriented programming system in R. So S3 classes are typically very simple. They have a very simple class system. You don't have any formal class definitions, and they're also something called single dispatch, which means basically if I use this method or call this a generic function speak, it'll only depend on whether the first argument is a cat or a dog or what other kind of animal is it. If I wanted to say for example, you wanted to implement some sort of conversation between your pets. So you had two cats speaking to each other. They might communicate differently than if you have a cat and a dog speaking to each other. So a cat and a dog might go wolf and meow to each other, and two cats just might meow at each other. But with S3, which is single dispatch, you can only change the behavior based on the first argument given to it. So you can't actually do something like that. Conversely, I'm going to talk a little bit more about multiple dispatch later on in S4. So another thing about S3 is its single inheritance. So each class, each subclass can only inherit from a single other class or chain of classes anyway. So for example, in S3, say you had a cat-dog pet. You couldn't have a cat-dog that inherits from both cat and dog because that doesn't make any sense, and S3 doesn't let you do that. So you can't have multiple inheritance in S3. So something is either a cat or a dog, or it's neither, or it's some other thing. So S3 doesn't allow multiple inheritance. Conversely, S4 is a more complex class system. You have formal class definitions, and you'll see what those look like in a little bit. But basically, it's more complicated than S3, but that also makes it more powerful in some ways. So S4 has multiple dispatch. So to go back to that earlier example, say you had wanted to have that conversation between two cats. If you had speak and you had two cats as arguments, they could both meow to each other, versus if you did speak to a cat and a dog, you could dispatch on both of those arguments and have the cat meow and the dog speak. So you can change the behavior of your methods depending on more than one argument that you pass to it, which can be really useful but also really confusing sometimes. But that's one of the things about S4, and we can talk more about that later again, but that's so S4, you have more complex class systems, formal class definitions, multiple dispatch, and also multiple inheritance. So in S4, if you wanted to have a cat-dog class, you could have a cat-dog class because in S4 you can inherit from more than one class. When to use which? In general, you want to use S3 for simple data structures without complex dependencies, and you want to use S4 for more complex data structures. Most of the classes that you use on a day-to-day basis when you're programming in R, a lot of those are going to be S3 classes, even if you don't know it already, but a lot of what you're working with already are S3 classes. S4 classes are a little bit more uncommon, and you don't see them as much in most of the packages you use on a day-to-day basis, unless you use a lot of bioconductor packages. Bioconductor is a repository that has lots of software specific for bioinformatics. So obviously, if you do bioinformatics, then you might use a lot more bioconductor packages, which has a lot of packages that use S4 class systems, because bioinformatics data tends to be more complex and have these complex networks of dependencies. So that's when S4 can become more useful than S3, when you have to have a formal class definition that reflects all of these complicated dependencies. So now we're going to look specifically at S3 classes. So S3 classes are created from base R types with additional attributes. So we'll see in a moment what attributes are, but first off, let's focus on that first part. S3 classes are created from base R types. So that means that S3 classes are based on raw vectors, integer vectors, numeric vectors, character vectors, and lists. So these are your base core R data types, and that's what S3 classes are based on. So all of your S3 classes will be, at its core, one of these types with some additional attributes tacked onto it. So S3 classes are defined by a class attribute, which you can access and set by the class function. So what are some common S3 classes you already use in R? As you can see, you probably already know this, but there's factor and DataFrame. So let's explore those a little bit right now. So here I'm just making a factor called FC for factor. You can just use class to get what class it is. We already know it's a factor. And as Jan demonstrated earlier, we can use type of to find out what the base R type underlying this data structure is. And you already saw earlier that a factor is basically just built on top of integers. So the type of factor is an integer. And if we look at the attributes, we find out that factors have levels and a class as attributes. And the class attribute is the one that actually defines what S3 class something is. Likewise, we can look at data frames, which I'm sure all of you have used already and are very familiar with. So the class of a data frame is just data frame. We know that already. The type of a data frame is a list. So at its core, a data frame is basically just a list where each of the list elements is the same length. The attributes for a data frame, a data frame has names, row names, and that class attribute data frame. So for example, if we change the class of this data frame object to a list, what will happen? Will that work? What happens if I just type df now? Come on, what'll happen? It'll just print out as a list because we didn't really change much to it besides changing its class attribute. Conversely, if I go back and just change the class attribute back to a data frame, will that work again? Will it behave like a data frame now? What do you think? So now if well, that part's working. I guess it doesn't want to print down here. There we go. Yeah, so we can just change, because a data frame is at its core just a list, if we change it back to a list and back to a data frame without changing anything else, we won't break anything. It'll just work. So S3 classes can inherit from other S3 classes simply by appending to this class attribute. So for example, you've probably worked with factors before, but you may not have worked with ordered factors. So ordered factors are just some kind of categorical variable that has an order to them. So I'll create an ordered factor here. It looks a lot like a factor, except it has a specific ordering to its levels. And if I look at the class for an ordered factor, it's just a character vector with ordered and then factor. So that's how inheritance works with S3 classes. It's basically just a concatenation of the first thing in that class attribute is the class that it is, and then everything after that is the classes that it's inherited from. So that's just a very simple introduction to what these S3 classes look like, and we're going to be writing our own S3 class in just a little bit. But first, we're going to talk a little bit about S3 methods. So as I mentioned, in R, methods are implemented using something called generic functions. So if you're familiar with object-oriented programming from a language like Java, you may be familiar with writing functions, for example, object.method call a method on an object. In R, it's a little bit different. Instead of methods belonging to a class, the methods belong to a certain generic function. So instead, you would call a method on some object. And that's, for example, we saw earlier how we can use plot or print, and plot and print behave differently depending on what kind of object you give to them. So S3 generic functions in R basically are just functions that consist of a body that just has use method and then the name of the function, or the name of the generic function. So we can see plot is defined just as use method plot. Likewise, print is just defined as use method print. So what do those actually do? Well, in order to find out what they actually do, we have to decide what kind of object we're looking at. So, but another thing though is that all of these will also have, not all of them, but a lot of them will have a default method that you can get by print.default or plot.default. So typically, most of the S3 methods will have some kind of default method that you have just the method name .default. And so you can see that S3 methods in R are basically just defined by this naming scheme with the name of the method followed by dot and then the name of the class. And that's really all there is to S3 methods. They're basically just this naming scheme, and R happens to have an implementation underneath it that allows it to find the correct method based on this naming scheme, which also means sometimes you can have confusing behavior, such as because R doesn't usually care about periods in names, so you can have so usually it doesn't matter if I just have something with a period in an object name. However, you can have confusing cases such as so to coerce something to a data frame, you use as.DataFrame. But what would happen if you had a class called frame? Then it's confusing because it doesn't know. It's unclear whether you're doing some method called as.data for a frame class or an as method for a data frame class. Or actually, sorry, I meant as.DataFrame.DataFrame. That's the full name of that. So so the method itself is actually as.DataFrame, and you can have different things on the end of that. For example, as.DataFrame.matrix and as.DataFrame.DataFrame, and so forth. And it can get kind of confusing with these naming schemes. So that's one kind of drawback to S3 methods, is that they're just dependent on this naming scheme, which is kind of easy to mess up if you're not careful about how you name things with periods, which is contrary to how things usually work in R, because usually R doesn't care if you have periods in names. So some common S3 methods that you already use in R are print. We already saw that one. Plot. Another one is summary. You can use the methods function to find all of the methods for some given generic function. So, for example, print, you can see there are a lot of print methods. So print just prints out things based on what kind of object you give to it. And all of these are the different print methods. So basically, whatever object you have in R, there's some method out there that knows how to print it. That's a good question, I think. Yeah, so those are ones that are actually not exported. So like if I do, so the first one here is print.ts, so ts for time series, I believe. But if I do print.ts down here, I can't actually find it. So that means that there's a print.ts method somewhere, but it's not actually, the print.ts method itself isn't exported to the user. So there's some package out there that implements print.ts, and R knows that it exists, but you can't directly access print.ts. Let's see. I wonder. Yeah. So if I use 3 colons like this, I can gain access to objects that haven't been exported to the user. So this is how you gain access to the hidden things that you're not supposed to have access to. So I happen to guess correctly that print.ts is in the stats package. So if I go stats : print.ts, then I can see what the print.ts method actually is. But because it's not exported by the stats package, usually you can't see it, which is why it has that asterisk there. So now we're going to learn how to create a class with S3 methods. Any questions before we start writing our own S3 class? Okay, so earlier we learned how to write functions, how to normalize, summarize, and plot proteomics experiments. These are things that we would like to do, again, whenever we get a new proteomics experiment data set, but we don't necessarily want to have to rewrite all of that code that we write every time we do that. So it would be really convenient if we had some kind of class and methods that would take care of this for us. So, like for example, why do we always want to have to write all of the code that we write to plot or summarize a proteomics experiment when we could just write plot and summary? And likewise, normalize is another verb that you probably want to do to a lot of different kinds of data sets. Normalizing data is generally a thing that you want to do. So that's a good candidate to be a generic function. That way we can write a normalize method that just all we'd have to do is say normalize and give it our data set, and then that would normalize the data set. And if we have, say, different kinds of data sets and we want normalize to behave differently depending on what kind of data set it is, then we can just write classes for those different kinds of data sets and just always write normalize, and it'll automatically do the correct thing if we write S3 methods for that. So in this section, we're going to create an S3 class called S3 proteomics experiment, and we're going to create an S3 generic function called normalize. And then we're going to write methods for normalize, summary, and plot. So because S3 classes, like I said, they don't have formal definitions anywhere. They're not really defined by anything except for having that class attribute. The first step is to just write a function that creates these S3 proteomics experiment objects. So based on our infinite wisdom about what proteomics experiments are like, we decide that a valid proteomics experiment should have at a minimum some proteins, some features, some intensities, some labels, and some runs. We can probably do better than that, but just for the sake of example, let's do that. Let's stick with that. And because it gives us a lot of things for free, we might as well inherit from DataFrame. So to do that, I've written this function, which it just takes vectors for protein, feature, run, intensity, label, and then I also wanted to give it the option of finding out whether the data has been log transformed or not. And then I've also included a ... to add any additional columns that you might have in your experiment. So here I'm just taking the list of dots and saving that in a variable. I want to check if the user actually passed anything in those ... dots. And then depending on if they do, I either make a data frame with all of those additional columns, or I just make a data frame with those required columns that we have. Then I'm going to add an attribute to our object called isLogTransformed, and I just assign that to whatever the user passes as whether it was log transformed or not. So why do I have this isLogTrans after the ... Can anyone answer that? We talked earlier about what happens when you put an argument after the ... What does that mean? What else? So yeah, so you don't expect that the default will change very often. What else does it mean? Yes. Yep. So it means that whenever you call the function, you have to explicitly name that variable. And in this case, it's also doing another practical thing. Can anyone guess what that might be? So as a hint, everything in the ... I'm assuming are extra columns in the data frame that we want for this S3 proteomics experiment. If I had this islogtrans argument before the ... and a user wanted to pass in additional columns and didn't name them, what would happen? So because this islogtrans is after the ... as we mentioned, you have to name it explicitly, and everything that you pass to the function that isn't a name, that doesn't have a name, will be assumed to either be one of these first 5 arguments: protein feature, run intensity, or label, or belongs to that ... So if islogtrans were here, for example, and I called this S3 proteomics experiment function, and I gave it six columns. So I gave it a protein, a feature, a run, intensity, label, and I gave it some additional column that was, say, subject. What would happen without naming it? What would happen? So if I just gave it a 6th column and I didn't name it specifically, it would assume that the islogtrans is equal to that 6th column that I want to add to the data frame. So by having the islogtrans after the ... it means ... only captures things that we want to be additional columns in the data frame. So we can kind of do this safely, knowing that if a user wants to change that argument, they'll have to name it explicitly. And if they don't name a particular argument, then we can safely assume that it's going to be a column in the data frame.
Because the default is illogical,
Mm-hmm.
would it throw an error if the input to it wasn't logical?
No, in this case it wouldn't, because there's nothing in the body of our function that actually explicitly assumes it's illogical. All we do to it is we assign it to an attribute of the object. It would be a good idea, however, to check whether it's illogical, and then throw some kind of error if it's not. So a better function would be so now here we're explicitly checking if islogtrans is illogical and saying that it also has to be length 1. And now we're throwing an error if that's not true. Oh, that's just saying or. So if it's not illogical, or if the length is not equal to 1. So in R, there's a difference between having 2 of them and having 1 of them. Having 2 of them is basically having a single pipe or a single AND is a vectorized version of these logical operators. So, for example, true, false, false, or true, true, false. So the single pipe is a vectorized version of it. So if you have a vector on both sides, it just takes basically goes vectorized and compares does or on the first element, then or on the second element, then or on the third third element, and so forth. Whereas the single or the double version assumes that everything is a length 1. So conversely, that's only going to take the first element. And sometimes that difference is important, both because in things like if-else statements, it expects that the length is only going to be 1. In older versions of R, it just threw a warning if you gave if-else something longer than a length 1 logical. I think in going forward, I think it's going to be an error now. Another useful reason is because with the I think with the double one is everything will be evaluated left to right, so that if you have, for example, something on this left-hand side or something on this right-hand side that depends on the left-hand side being true or false, if this were and this were false, then this part would never get evaluated. So basically, if I have with the double ands, if I have two expressions here, if these were expressions rather than just explicitly true or false, and I had something in the second one that I did not want evaluated unless the first one were true, this would be safe to do. So because in this case, if the first one is false and you're using an and, then the second one will never be evaluated because it already knows enough to know to just say that it's false.
So like you were checking for infinite recursion in there.
Yeah, something like that. Yeah. So basically, if you need to assume that the things on the right-hand side will only be evaluated in certain situations, depending on what's there. So it's safe to do that with the double ones because it evaluates them one by one. So after assigning that attribute here, we then just assign the class attribute to it using this class function. So you'll notice that even though class itself is an attribute, and I've changed this other attribute for whether it's log transformed or not using this attribute function, I still change the class using this class function. And there are certain attributes that are kind of protected that you should always use their specific accessors to do this. Class is one of those. Other ones are dim. I think dim names probably, but you can see what they are by looking at this documentation for most attributes. Because yeah, there are certain attributes that have special meaning in R. So those are dim names, and usually also class, comment. The rest, all of these are hard to see, but so some attributes are treated specially and have restrictions on which values can be set. So you should typically only change those with their specific functions, because then R will do that error checking for you and tell you if it's an invalid value for that particular attribute, because R already has certain expectations about what will be in a class attribute, what will be in a comment attribute, what will be in a dim attribute, and so forth. So for those, it's a good idea to use the class or the dim names accessor and setter. So after assigning the class to it, which I do just calling it S3 proteomics experiment, and then DataFrame so that it inherits from DataFrame, then I just return the object. So I'll just run that. Now, if we get our data set, I'm just going to rearrange it real quick so that it's in a format that we can use. So basically, I've just I think Seung-Heng showed this as an example earlier, but basically I just rearranged it so that it has an additional column for a label that instead of separate intensity columns for heavy and light, it has one intensity column and then a column called label that says whether that particular row is a heavy or light channel. So now I create our S3 proteomics experiment object and call it twin DIA3. And our studio is being weird again. So I can just call head on it like I would on a data frame, and because we inherited from data frame, we get all of the behavior that we would expect from a data frame. So now we're going to write a function or an S3 generic function for normalize. So normalize is not already an S3 generic function, so first we're going to learn how to create an S3 generic function. And it's really simple. As we saw earlier, an S3 generic function just basically is a function with a body, use method, and then the name of the generic function. So here we're just going to create a function called normalize, and the body is just going to be use method normalize. So I'll create that. And now I'm going to create a normalized method for S3 proteomics experiment objects. And doing that, I just follow the naming scheme normalize.s3 proteomics experiment. So here I'm basically just doing that one of the median normalization that Seung-Heng presented earlier. And here I'm also checking whether the data set has been log transformed or not. And if it hasn't been, then I'm log transforming it. As an exercise, it would be a useful thing to, for example, add an attribute that keeps track of whether the experiment has been log transformed to using log2 or log10. So that would be a neat thing to do for an exercise. So you would add an attribute that either keeps track of, say, the base of the log, or for example, or just whether it was log2 or log10, or what kind of function it was used to normalize it. But here we're just assuming that if it was log transformed, you want log2. Then we're getting so I have this argument by, so that's going to be the label for the standard that we're going to use. Checking which rows correspond to that label. Then I'm getting the medians, getting the median of the medians, and doing that median normalization that Seung-Heng presented earlier. We'll also write methods for summary and plot. So here's summary. For summary, we're just gonna, so summary already exists as an S3 generic function, which we can see just by writing summary. We can see that already exists, use method summary. And so we can just write summary.s3, .s3 proteomics experiment to create our S3 method for it. And this is just doing a sum over the feature intensities to get a summary that way. And now we can write a simple plot method. Now, in reality, you would probably want to write several different plot methods depending on what you are interested in writing about. But here we're just going to make a box plot of the intensities. So now we can just call normalize on our data set. Say we want to normalize it by the heavy channel. We can get the summary. Oops. Let's see, what is this error? That looks fine. So somehow the intensity has become a character. Where would we have done that? Oh. Who knows what happened? So Jan played a practical joke on us, apparently. So the problem here is the plus operator is still redefined to pasting two strings together. So all of our intensities are now strings. Okay, let's restart our. We probably could have just removed it, but.
It's still identified. You need to, yeah. You want, before you restart in RStudio, you need to clear your workspace.
There we go. Delete everything. Okay.
If you want to make it really simple, you can just do the run drop down and click on run all chunks or run all chunks above current chunk.
Okay, let's see, where were we? Okay, so we still need to define our normalize again, and our summary under plot. Now we can normalize it, and there. Now that we have the correct addition, okay, and we can also just run plot on it, and that'll just plot box plots of the intensities for each run. So that's just a really simple, quick example of how to write S3 classes in R. So I'm going to move on to talking about S4 classes now. Does anyone have any questions about S3 classes before we move on? Yes? Mm-hmm. Oh, so you mean if I wanted to plot something? Well, let's find out. So let's see. We'll just plot a really simple thing, and that just plots like it's supposed to. So the answer is no, because what we defined was a plot specifically for our S3 proteomics experiment class. It doesn't interfere with any of the other plot methods. So plot for everything else is totally unaffected. Well, in this case, the reason, the whole point is so that we can just say plot on it, and it'll only do our plot method if we give it an S3 if we give it an S3 proteomics experiment object. So if we wanted to do some other kind of plotting, we would just give it a different kind of object. And we assume if that we're giving it an S3 proteomics experiment object, we want to do the specific kind of plotting that we defined for that specific class. So just for a quick example of how we could do the same thing that Jan demonstrated earlier, but without breaking everything, let's define an S3 method for addition. Now, as I mentioned, you can have a default method That's just the name of the method .default, and I'm just going to make that the actual addition function that is, or actually base, I believe. Yep, the actual R's normal addition. And now I can define one for character vectors. So now I can check 1 plus 1, that still equals 2. A plus B, that paste together A and B. So this is an example of how you can use S3 methods to do the kind of thing that Jan was doing earlier to concatenate strings, for example, to concatenate strings using the addition sign, for example, without breaking everything else in R. Yes? Mm-hmm. So sometimes, so that'll if you just write, not every function is going to be a method. So sometimes you just have functions that have the same name as each other, and in that case, then you will have so and so was masked by this new name. So if it was an S3 or an S4 method and it was just implementing a specific implementing that method for or that generic function, a method for that generic function for a specific class, then you wouldn't get that message. But if there's already an existing method with already an existing function, a regular function with that name, then it'll mask that. So for example, if I wrote a package and I had this code in it, then you would still get a message that the plus operator has been masked, because I'm redefining the primitive base plus to be this S3 generic function plus. Yes. Yep. So there are a lot of S3 methods in dplyr, but in some cases, I believe. Let's see. So I'll just that loaded without. So in this case, I'm not getting any. Okay. Okay. Yeah. So here, for example, arrange in plyr, it's just a regular function. You can see because it has all of this code for instead of a use method or in the case of S4 methods, it would also look different, and we'll see what that looks like in a moment. But arrange is just a regular function, and if both plyr and dplyr have regular just functions called arrange, then you're going to hide one of them. Well, in the case of tibbles actually are just, for the most part, are just regular data frames. Structurally, all of the differences are just implemented in the constructor for them. For example, the DataFrame constructor always adds row names, whereas the tibble constructor does not add row names unless you specifically ask for them. But a tibble inherits from DataFrame, so everything that works on one will, for the most part, work on the other. Yes.
And I also want to point out, if your functions are being masked by another package and you need both packages, you can always explicitly call the function from the masked package. That's not a big deal.
Yep. So for example, here I can just use these double colons to get the specific arrange from either plyr or dplyr. Yeah. So I think for the most part, assume you're not going to be using both of them together. But yeah, for things that are just regular functions, they're going to mask each other like that. Or even if you're redefining what the generic function is. So you'll notice, for example, that the generic for plot has this particular signature x, y, dot, dot, dot. If I redefined it to have, say, object instead of x, y, if I just renamed that argument, then that would also change things. So whenever you write an S3 or an S4 method, it's going to also inherit those arguments, those parameters. You can add things to them, but it has to match that for the most part. Yes.
Can you call some methods for specific classes on an object that is not that class? Like, for instance, doing the 1 plus 1, but calling the plus character method instead.
Yes. So does anyone want to guess how to do that? Okay, so to call the character version on numbers, for example, I could just do this. So Jan probably talked about how all of these infix functions or infix operators in R like plus are actually just regular functions, and you can call them like regular functions. So here, the name of my method for this plus is just plus.character, and so I can call it using just plus.character surrounded by these backticks and then the arguments. And so if I do that, and of course because it's R, it coerces them to characters, so it ends up working. But yeah, so yeah, you just have to use the full name, the plot dot whatever, print dot whatever, and then.
So like in the case of like proteomic experimenting, if you wanted the normal data frame summary, you do
Yep. So. What did we call it? 20i3. Yeah. So there you go. You can just get the normal summary or whatever else you want by just calling it with the full name. Okay. So now we're going to move on to S4 classes. So S4 classes are more rare in base R, but they're more common in bioconductor packages. And like I said, that's mostly because with bioconductor, they're dealing a lot with bioinformatics data sets, and so there's this more complex system of dependencies. You have complicated experiments, so you want a more complicated, a more powerful object system be able to account for all of those complications and complexities. So S3 classes have formal class definitions and more rigorous structure. So if you're just doing something simple on the fly, then they can be a lot more tedious to use. But if you happen to need that additional power, then they can be very useful. So S4 classes are defined by a set class function. So with S4 classes, you actually have to define what a class of that particular kind looks like, and you do that with the set class function. Rather than deriving from the base R types like S3 classes do, S3 classes are based on lists or numeric vectors or things like that. S4 classes instead have slots, and these slots you can define what kind of types are in these slots, and you can also define a valid object method, which will basically check whether an object is valid or not. And you can define what that means specifically for your class. So we can look at class definitions with the getClass function. So even though DataFrame itself is an S3 class, R also provides an S4 version of it in case you want to do S4 stuff with DataFrame. So since we're all familiar with DataFrame, we're just going to look at the S4 version of DataFrame. So the S4 version of DataFrame, you can see it has these different slots. So the slots for the S4 version of DataFrame are .data, which is a list, names, which is a character, row names, which is this special class called DataFrame row labels, and .s3 class, which is a character. So you can kind of see some rubble from the S3 system in this S4 version of DataFrame, but it'll work for our purposes. And you can also see what classes the DataFrame extends.
Is extends essentially inherits?
Yeah, so extends is what class it inherits from. Yep. So now we're going to define an S4 class called S4 proteomics experiment, and again we're going to inherit from DataFrame. So we do that using this define class function. The first thing we give it is just the name of the class. With S4 classes, you define what the superclasses are or what classes it inherits from using contains equals. So we're just going to contains equals DataFrame. If we wanted to inherit from multiple things, we could make that a character vector with a bunch of different classes we wanted to inherit from. But in this case, we're just going to inherit from DataFrame. Then we have different slots. So we have slots for this islog transformed or not, and a slot for title. So because we feel like having an experiment title would be fun. So we're going to have a slot for an experiment title, and that's going to be a character. And here we can specifically say that whether it's log transformed is illogical without having to define that somewhere else. We can make that explicit here. So we're going to define a validity function here. So that's just defined with this validity. And here I'm going to list what columns are required for it. I'm going to check if any of those are missing. And then if any of those columns are missing, I'm going to print out a message saying it's missing those columns. And otherwise, I'm just going to return true because it's a valid S4 proteomics experiment. So if you'll notice over here, you can see that the slots in S4 classes are accessed using the @ symbol, which is really different from S3 classes and most other objects in R. So typically, you don't actually want your users accessing those slots using that @ symbol. That's even though R doesn't make those explicitly private, it's good form to provide some kind of accessors to those rather than accessing things via @ in anything besides your own functions that implement the class. So typically you would use names object and names object equals value to assign those things. So here, another thing is that S4 objects can just be created with this new function, which you can see here, but it's still typically a good idea to provide some sort of constructor so that your users aren't having to call this new function, which can be kind of clunky. So here I'm doing basically the same thing as before, but creating an S4 object with this new.
You're missing the S.
Thank you.
So R is not actually figuring out anything because we started the name of our class with S, right? It's all in how the function is.
Right, yeah, that's just for our own convenience, yeah. The actual name doesn't matter. So here we're using our constructor to create an S4 object, and our studio being weird again, but we can look at it, and again we get the same DataFrame behavior that we would expect because we inherit from DataFrame. S4 generic functions are defined using setGeneric. And you can also use getGeneric or isGeneric to find out whether something is already an S4 generic function. So here, I'm just going to see if these things are already S4 generic functions or not. The answer is no, yes, and yes. Actually, I think that might be new in this version of R, so because I had these setting generic before. But in any case, it doesn't change anything. So when a function already exists and you want to just make an turn it into an S4 generic function, you can just do that by calling setGeneric and then the name of the function. and then that'll just convert it into an S4 generic function using the existing version of it as the default method. So now, if I do get generic on these, we have these things which show that there are S4 generic functions with the standard generic, which is just basically the S4 version of use method. So these are now S4 generic functions, in addition to already being S3 generic functions. And we can find that out by, so show methods will just list the existing methods for normalize. The only one is this default one for object equals any, so that basically means object can be anything, and so that's the default method. We can find out what that particular method is using select method, and if we do that, we find out that it's actually our S3 generic function. So that S3 generic function still exists somewhere. It's just the default S4 method now also. So now we can define methods for those just using set method. So with set method, the first thing is just the name of the method and then the signature. And so this is basically the classes that will appear in the argument list. And you can see here, for example, for plot, methods may be defined for arguments x and y. So that means for plot, you can have multiple dispatch on both x and y. So the method that will be selected when you call plot can depend on both the class of x and the class of y. And that's what you would put next here in this set method. In the case of normalize, we're only defining things on the first argument, so all we need is give the class for the first argument, which is an S4 proteomics experiment. You'll notice when we do the same thing for plot, we actually also just give the first argument, and that's because if you don't give any additional arguments, it'll assume that the rest are also this special any argument. So I can just define these S4 methods just using set method, giving the name of the method, the class, and then a function. And those are just the same functions as before. And now we can just call normalize, summary, and plot on our S4 class as well, and that all works just like before. So that's basically a quick introduction to S3 classes and S4 classes. I actually went over a half hour, so I apologize for that. But I'd be happy to answer any questions since I'm here till 6 anyway. So, yes?
Because you define plot normalize as both S3 and S4, right?
Mm-hmm.
So whenever you run it, by default, if both are defined, which one does it choose?
It depends what class you or what kind of object you give to it. So if I call plot and its argument is the argument that you give to it is an S3 class, it'll go find the correct S3 method for that S3 class. If it's an S4 class, it'll find the correct S4 method for that S4 class. Yeah, so it'll all, for the most part, just work. Mm-hmm. Yes?
You know that clock isn't right.
Oh, it's not?
Yeah, you're actually half hour early.
Oh, okay. Okay, then we can do anything we want. What do you want to do?
Let's solve an efficiency problem. Actually, I have a
Yes.
general stupid person question, and what comes down to why I always hated object-oriented programming.
Mm-hmm.
It seems like it's very easy to get the methods. Like if you have you can get all the methods that are associated with plot or something.
Yep. Mm-hmm.
But I typically want to do the opposite. I have a class,
Mm-hmm.
and I want to get all the accessor methods associated with it. I'm the guy who's always pulling things out with the add.
So you can do that just by using the methods function and class equals, and then just give the name of the class.
So if you're starting with like just like the object, like you have like twin dia 4, class.
Yeah, so I can just do twin. I don't know what happened there. It's because yeah.
Oh, right.
Because class for the S3 class for that prints out both the full vector of S3 experimented data frame. But yeah, so you can just do that, or for and those are all the. So for this one, it ends up having more just because it'll automatically show more things that were inherited. Or in this case, it has some things that just all S4 objects have, like this initialize method. So it ends up showing more here. But yeah, so to answer your question, you can just use methods, class equals, and then that, and then the name of the class. Yes?
So this could probably get covered tomorrow, but how do you make documentation on that to generate when you're writing in class?
So that will be covered tomorrow. So I won't spoil it yet.
I learned about Java
There is a package that does that, yes. And we'll talk about that tomorrow. Yes?
Okay, this is also, or this is not, this is also kind of a stupid question, but so going back to your set generic and get generic statements for the S4 methods for normalize and summary and plot, they'll create these functions for this S4 object, for the as an S4 object. But and then set methods. Okay, never mind. I think I figured. So the set method statement applies these functions that we've added to the S4 environment to our particular S4 proteomics experiment. Is that right?
Yep.
Okay.
Yeah, so S4 classes are definitely a little bit more complicated than S3 classes and methods, but there can be times when that extra rigor and formality can be really useful. And like I said, there's a lot of S4 classes on Bioconductor, and so when you have a complex experiment and you want to make sure all of the rows are correct, all of these samples have associated descriptions and things like that, then being able to check whether an S4 class is valid or not, and being able to model all of those additional constraints and complexities can be really useful. Yes? Any of you? Anyone?
So I have been led to believe that when languages are designed, usually they're designed as a certain type of language. Like I've been told R is a functional programming language, and Java is an object-oriented programming language, or something to that effect. But now we're talking about using objects in R. So is that just a gross oversimplification, or is that really a thing, but objects are really useful, so they've been added to a lot of languages?
It's a little bit of both. Most languages will have a certain guiding principle, guiding design that will kind of guide how they are developed and how they're designed. And yes, so R or S before it and now R is largely a functional language. So functions are first-class citizens. You can manipulate functions just like you can any other object, and so forth like that. It's R also has this immutable state that Jan was talking about. So it assumes that it assumes that your objects aren't going to change, and that gives you certain things like ideally it would give you a certain level of functional purity. That's not actually true, but in R, because you have side effects with things like print. But it's designed primarily as a functional programming language, whereas yes, Java is more designed around object-oriented programming. In R, everything has to be an object. Everything is a class. That's true to a certain extent in R because everything has some kind of class behind it, but it's not true nearly to the same extent as Java. And yeah, you can kind of tell just by how they work that the object-oriented systems in R, S3, and S4 have been kind of added later after the original language had already developed quite a bit. You can tell that just by the way that the S3 class system works, just because it's basically based on this naming scheme that kind of conflicts with how lots of other things in the language are named. Why do you have as.DataFrame, or even just why do you have DataFrame with a period in the middle of it when S3 methods are defined by a period dividing the name of the generic function and the class? So you can kind of see in places like that how object-oriented programming kind of came as an afterthought to R, and there's definitely things that I like about the way R implements object-oriented programming, but it is not as central to the goal of the language as it is for something like Java. And there are definitely some other differences just in the approach to object-oriented programming with a functional language like R. And that main one, as I mentioned earlier, is how in Java you would have object.method to call a method, or else in R you have the method and then the object. So all of the methods are functions first. They belong to the generic function rather than the specific object. So even with when it comes to object-oriented programming in R, it's primarily based around functions and these generic functions that then can be applied to different kinds of classes. And but there are also other types of object-oriented systems that I didn't talk about that are so there are a couple different packages on CRAN that implement object-oriented programming in R in ways that are more similar to Java and C++ and so forth. And there's also another one that comes with R also called reference classes, which I didn't talk about because they're not used as much. But things like reference classes are more similar to the kind of object-oriented programming that you would get with Java. So with reference classes, you do end up doing things like object method to call a method. So if object here were a reference class, you would call methods by using this way of calling the method. So it's a lot more similar to something like Java or C++. One of the other main ways that S3 and S4 are different than some of the other object systems in R is that S3 and S4 keep with this functional programming idea of immutable state. So S3 and S4 objects are basically intended to be immutable. So if you go and change something in an S3 object or an S4 object, it'll copy the object, just like Jan was showing earlier with other kinds of objects in R. So you have that same kind of behavior with S3 and S4 classes. So basically, and that can be nice in certain situations. So like say you get past some S3 or S4 object in a function, you can go modify it at will, knowing that you won't have any side effects to whoever is using that object elsewhere, because you'll get your own copy of that object that you can do whatever you want to. So that's something that this idea of immutability gets you, is that you can do whatever you want with an object inside a function, and it won't affect that object anywhere else. With things like reference classes, which behave a lot more like Java, reference classes, and there's another package on CRAN called R6, which is another object-oriented system that's very similar to reference classes and calls methods in this same way. These implement object-oriented programming a lot more similar to Java, and they have mutable classes, if you pass the object to some function, that function can then modify the object, and you'll see those changes update in your own object wherever else it happens to be. And so that can be both good and bad. It can be useful in terms of memory, so you don't have all these extra copies of data running around, which can create a huge problem in R because you get a bunch of, if you end up creating a bunch of extra copies of objects without knowing it, that can really create a lot of memory overhead that aren't necessarily expecting. Whereas with mutable objects, you can update things in place and not expect that to suddenly blow up your memory. However, that also can create some problems in terms of user expectations because our programmers are used to things behaving in certain ways, and when you do things differently, like with reference classes and R6, that kind of breaks the expectations of what our programmers are used to. So if you pass some object to a function, you generally expect that function either isn't going to actually be able to change your own copy of that object. But with mutable objects like reference classes or R6, that can happen. And the same is also true if basically all of these things are implemented using environments mostly. And so, and I believe Jan talked about environments on the first day. So E is some environment. I'm going to store 1 in this environment. I'm going to create a function that takes some kind of environment and modifies something called x in it. So here in my copy of E, x is 1. If I do foo on that, then I can see in my version of E, x has been changed to 2. And so that's the kind of behavior that you can do with environments and also happens with these other versions of object-oriented programming like reference classes and R6 that doesn't happen with S3 and S4, which can be really useful but also just kind of breaks user expectations with how people are normally used to programming in R. But sometimes they can be really useful. So if you are interested in that kind of object-oriented programming in R, you can look up these reference classes or also packages called R6, and I think there's some other ones called like R.oo, and people are always coming up with new packages for R. So that was a long answer to that question. I hope it was helpful. So, yes?
So this is kind of a reproducible research question, I guess. So let's say you have a bunch of functions that you use to analyze your proteomics data, like these ones we made. And you have them like on your local machine as your own package. How would you suggest like sharing those and say like to share your analysis for like publication?
Generally, the best way, if you have some kind of collection of functions that you have as a package on your local machine, the easiest way to do that is just distribute your package, which you can either do very easily just by hosting it on GitHub or also submitting it to CRAN or Bioconductor or another repository like that. And if you send it to CRAN or Bioconductor, that also makes it easier for other people to download, because those will take care of all the dependencies and make sure everything is installed correctly for whenever users download it. And we'll talk more about building your own package tomorrow as well. All right, so that's it for today. I guess we'll end 10 minutes early. I will hang around for a little while longer since I'm supposed to, if you have any more questions. Otherwise, I'll see you tomorrow morning. I'll be here, Singheng and I will be here at 8 a.m. if you have any other additional questions tomorrow morning. And we'll start at 9 a.m. tomorrow with JJ Allaire's keynote. Thank you.